Welcome to my new calculus channel. I am John Gabriel. In this YouTube episode, I'm going to be discussing Newton and his infinite series. Before I begin, I'd just like to tell you that whether you're a renowned mathematics professor or a high school student, you will learn things in this video that you've never known before, you haven't even dreamed of, and it will cast a whole new light on your perspective of those mythological objects you think of as infinite series. Well, infinity is really a junk concept. It doesn't exist in any shape or form because it cannot be reified. But it has taken root because of the unfortunate actions of great mathematicians like Newton. Well, what Newton was working with were not infinite series. They were actually partial series. And I'll explain to you in a short while why they were not infinite series, and indeed how all the series that he worked with could be written in closed form. So you may or may not have heard that expression, closed form. That means anything, for the purposes of this video, it means anything that doesn't need that written at the end, an ellipsis, okay? Newton began his work in the Analysi, his famous work on calculus. The Analysi, I think it's spelled like that, it doesn't really matter, in which he describes how he derived the formulas for sine x and sine and all the other trigonometric ratios. He actually derived the series, which can also be written in closed form. Yes, that's right, you heard correctly, they can be written in closed form. I'm about to show you some examples, and I'll tell you also that they can be written in closed form using the Gabriel polynomial, but I'm not going to be discussing that in this YouTube because it's an entirely different topic. There is a video out there which talks about the Gabriel polynomial, and you can watch that and study it if you wish, but I'm going to be staying to slightly more simple concepts in this presentation. So let's get rid of that. Now, Newton was doing a lot of things with approximations, and one of the things that Newton was dealing with is this sort of problem: how to write this in a way that it could be approximated, and then to move one step further from this. In other words, from here to something like this. Okay, both these ratios can be written in closed form. I'll show you in a little while how that can be written in closed form too. It's a little harder, but I'll show you how it can be done. Alright? So let's just start with a simple one for now. So what Newton did was he said, okay, well, let's just try long division. Well, I guess Newton was living at a time where a lot of things were still unknown, didn't really have anybody else's work to build on, so one can't really say that he was doing something stupid, but his choice of terminology was very unfortunate. At any rate, if we go by this particular process, what we end up having with here is oh, that's wrong, is A is A over B. We say B divides A over B, and then we multiply it out like so. Okay. And we subtract the two, and we have minus AC over B. Yes. And we say, how many times does B go into minus AC over B? And we find that it goes in minus AC over B squared. Okay, and we continue this process. So that gives us minus AC over B and minus AC squared over B squared. And the next one is going to be plus AC squared over B cubed, like so. And if we multiply it out, we get that plus AC cubed over B cubed. And finally, I'm going to stop here now because you can carry on like this ad infinitum, and I don't want to do that. So basically you can see the pattern emerging here, so that the next term would be AC cubed over B4, right? Okay, but this is the unfortunate part where Newton put a plus sign and an ellipsis there, okay? That's unfortunate, because this can be written in closed form. And so how do we write it in closed form? Well, remember that this here is the remainder, isn't it? So the remainder would be this divided by the divisor, which is B plus C. Is that not right? That means we could effectively write this as, in other words, A divided by B plus C as let's see here, as A over B. Oh, that looks like a 9. As A over B minus AC over B squared plus AC squared over B cubed, like that, minus, and it's this term divided by B plus C, right? So we'll have AC cubed over B cubed times B plus C. And this will work regardless of the value of A, B, and C. Doesn't matter what these are. They can be any number. This is true. And this is the closed form, but it's not the only closed form. Well, for example, if I had used those first four terms, then I would have had all those on this side plus an extra term resembling something like that. In general, we could write down that A over B plus C, in general, let me give you a general formula, is A over B minus AC over B squared plus AC squared over B cubed plus, there are a finite number of terms here, so this ellipsis doesn't mean infinity, okay? Minus 1 to the n AC to the n over B n plus 1. And this is the general, I thought I'd gotten the box there. Okay, let's go again. Got it. Okay, so now, so that's the general form of this ratio here. And we'll see that we can approximate its value by just taking the terms as far as we can calculate them. We don't necessarily have to calculate the complete closed form. So this here is the approximation, and if we add the final term in, that would be the closed form. Okay? So this whole thing here is the closed form, and this here is just the approximation. I don't know whether Newton knew this, but I strongly suspect he did, and I don't know why he decided to call these infinite series, because, well, as I said, it's a stupid term. And infinity is a junk concept. So now, some problems arise when you begin to throw away this function here. Okay, let's call that f of n, and there's a reason I'm calling it f of n. You'll find out in a little while. Actually, if you had to use the big O notation, it would be O followed by whatever the approximation is going to be here, the integral power of the approximation. Usually it's denoted by x and some integral power, let's say 4 or something. So it would be of order 4 in this case, right? Or of order 5 or 6 or whatever. But Fn in this particular case is not determined by limit theory. It is a precise function which gives an exact value. So there is no need to use the rot of limit theory here at all, as you see in this particular description here on MathWorld. For example, you'll see the big O notation is the inverse of the big omega notation. So this obfuscated junk really tells you that Fn here is a particular function which you come up with, which is not an exact function, but you can have the exact function because closed form is possible, as I've showed you here. And I'll show you in a little while also that on MathWorld, where because I'm going to be showing you how to find the closed form version of this is the big O notation here, and this here is actually f of n. There is an exact function for it, so it's not even an approximation. This is using the Taylor series, which has an error term. The Gabriel polynomial or the Gabriel series has no error term, and it is always finite, even though the number of terms are variable. Okay, so now that we've looked at that, I want to come back to what I said earlier on about this. Just dropping away this Fn function here can cause problems when we're dealing with a finite number of terms, or a partial sum with an ellipsis at the end. And so we'll get restrictions. So for example, the restrictions in something like this, where x is a variable and k is some number, will be that the absolute value of x must be less than k. In other words, x must lie between k and minus k. Okay? So that's the only time that this approximation here will give you correct results, unless you have the closed form, in which case you will get correct results every time, regardless of what the values of k or x are. Okay, so where do we go from here? Right, now I want to look at something else now, also still on the same topic, but just let me make some space here. Alright, delete that. Okay, very good. And so, get the pen back. So now you'll see that in Newton's derivation of arc length, I don't know if you've ever studied that in his famous manuscript Analysi, where he uses this diagram and shows how to arrive at the arc length formula. Okay, the arc length formula is actually the integral of 1 divided by 1 minus x squared with respect to dx. That's the arc length. But Newton didn't use calculus to find this, and I'm going to show you what he did and how he got to where he did, and also some problems with it and how you can deal with it. So, now Newton decided, well, he was going to do something like this. Oops, I don't want a line, I want that. Okay. So, he said, well, let's do this. Let's divide 1 by 1 minus x squared over 2 minus x4. It's hard writing with this tablet. Okay, so that's x squared minus x4 over 8 and minus 5x squared over 8 all over 128 plus dot dot dot. Okay, so then you do the long division, the so-called long division algorithm. It's not really long division because it's not closed form, but we have that, and if you multiply one by this, which happens to be a partial series representation of 1 minus x squared, then we have 1 and this whole thing here again. Okay, I'm not going to write it all out. I'll just do that. And then Newton subtracted these two and arrived at x squared over 2 plus x4 over 8, etc. Right? And again, he got the next term, which was that, x squared over 2, and so on. And it turns out that you can actually use this inside the integral to find the arc length series. But now what I want to show you is that you can actually do this using closed form. And the way you would do it is as follows. You would have 1 divided by 1 minus x squared like that, which gives you 1, right? So that multiplied is 1 minus x squared. Yes. And that gives you 1 minus x squared. And then multiply the next term, which is plus x squared over 2 by this to give you minus x squared over 2 times 1 minus x squared. And if we subtract these, we get 1 minus square root of 1 minus x squared times x squared over 2 plus 1. And now we can write the closed form as I showed you earlier by simply saying it's this plus the remainder divided by the divisor. So the closed form would simply be this, 1 plus x squared over 2 plus 1 minus x squared, the square root of that, times x squared over 2 plus 1 all over the square root of 1 minus x squared. And this here is the same as writing 1 plus x squared over 2 plus x3. In fact, this here is equal to exactly fn. The particular fn that they're talking about here on Math World is not equal to that. It's just something that approximates that, okay? So that function fn is not the same as the one I'm describing here, which is exact. This here is exactly fn, and this here is exactly equal to 1 over the square root of 1 minus x squared. So this is the closed form. And there is no need to have big O notation or use limit theory to worry about the approximation error. It always puzzled me when I read during my teenage years topics on the error term in the Taylor approximation. And I've seen so many YouTube videos, and they're filled with mistakes, and they just show the ignorance and stupidity of those who compiled those videos. They really don't know what they're talking about. And there is really no need to be able to determine, to use big O notation or limit theory when you can actually write every series in closed form. Okay? So, I bet you didn't know that. You may still not believe it. Of course, if you don't, you're an absolute moron. But that's besides the point. So, let's just say that is what I wanted to discuss with respect to Newton and infinite series, Newton was a master of approximations, okay? He really was just so into approximations that I think he forgot the overall idea of what's required in mathematics, which is to be exact, to be able to find the exact values. And of course, everybody who came after him really followed in his footsteps. For example, Taylor and Maclaurin. The Taylor series is vastly inferior to the Gabriel polynomial. Okay, vastly inferior, and you can read up about that in the Gabriel polynomial YouTube video. In fact, while the Gabriel polynomial was not designed for approximation, it outperforms the Taylor series expansion for every given function, for any given function, in fact. So that's pretty much it. I don't think there's anything else that I need to add here. Coming back to this diagram here, as I was showing you earlier, this here is an exact function, fn, so it can be written in closed form. Math World doesn't know about it because this is the first time I reveal it here in this video. No other moron professor dare say they knew it, because there is no record of it being written anywhere, so they would be violating copyright if they went ahead and said that they discovered it, as I'm going to be uploading this video to YouTube in just a few moments. Very well then, I hope you've enjoyed this presentation and were a little bit entertained by it too. You have a lot of work ahead of you. This theory is not very easy, and probably most won't get it, but some will get it. This is the New Calculus channel. I am John Gabriel. Till next time.